So I'll begin with an example. X be a uniform random variable from 0 to 1, and let say real numbers be defined as g of t is equal to 2t. If 3/4 less than or equal to t less than or equal to 1. Okay. Now find the distribution function of g of x. Okay. So this illustrates some question that was asked last time. So I want to explain this. So you just write down the definition. So probability of y less than or equal to little y. Okay. So this is so y is equal to g of x. So you write this in this following fashion. So this is probability of g of x is less than or equal to y. Maybe you want to write one more step so that it becomes clear. So this is the same thing as saying probability of the set omega such that g of x of omega is less than or equal to y. Okay. And if you call this equal to x, so let us just call, so let so g of, so x of omega suppose is equal to x, then this is same thing as probability of the set of all omega such that g of x is less than or equal to y. Okay. And now you ask yourself, okay, what is the values, permissible values for y? Y takes values where? So y takes values in the image of the unit interval, that is image of g. So actually y can take any value, but what happens, what is important is that g of this must be less than or equal to y. So you just note here, let me explain this. It doesn't matter if I take a little bit time. So this is a real line. Y is somewhere here, but let us mark off these special intervals. So 0 to 1. Okay. And then I have 2, and this is 3. Okay. So depending on where y is, Suppose y is here, so we can now write, therefore p of y, having written up till here, now it's a very simple matter. P of y less than or equal to y, this is equal to 0 if y is less than or equal to, y is less than 0, let us say. And then if it is somewhere in this interval, okay, y is somewhere here, let us say, okay, then I must look at all those values of x. So all those values of x which get mapped onto this. So it's like g of x, that is 2t equals y. So that that's a portion that is going to be relevant because I'm assuming. So now let us suppose that 0 less, if 0 less than or equal to y less than or equal to 1, okay, then uh, the inverse image will be exactly 0 to half, no, 0 to y by 2. G of this is what is getting mapped to 0 to y, okay, and below that of course is 0. So this is probability that I can rewrite it, okay, probability that x is less than or equal to y by 2, okay, and so that's equal to y by 2 because I have uniform distribution. I'm not done yet. And now suppose that it exceeds this, then it in fact stays this way, in fact up to, but excluding 2. So I can even write here, just one go I can write. Okay, so let me not change that. This is the case. And this is also equal to y by 2 if y is strictly less than 2. And then there is a jump. When y equals to, what happens? Y equals to, you see this, I must draw here the domain. I draw it in some other color. So this is 0 to 1. Okay. This whole interval, this bit had gone to here. And the next bit from here to here, okay, this portion, entire portion gets mapped to 2. Okay. This gets mapped to 2. So the moment you include 2, set of all x so that g of x is less than or equal to 2 would involve all the way from 0 to 3 quarters. And it doesn't really matter whether 3 quarters is included or not. The way I defined it, it is not included, but it's not going to really matter so much. So if so this is going to be equal to 3 by 2, 3 quarters if y is less than 3 by 2. Okay, so 2 less than or equal to y less than 3 by less than or equal to 3 by 4. It doesn't really matter whether you include that or here. Um, mm, no, sorry. So this is up to 3. Up to 3, it is this way. Why up to 3? Because the next value that is assumed is actually 3. And when 3 is assumed, it is 1. Y is bigger than or equal to 3. So you see, this is the function, and it is not a continuous random variable because it has atoms. No, so when you put, for example, so note that probability that y equals to is actually equal to, so this minus probability y less than 2, which is actually uh, 1/4. So therefore y is not continuous. Okay, so yeah, this is a good example to remember. You could actually make whatever you want, more or less. I mean, you can make y actually discrete, and it's also possible to make y neither. Yeah, this is an example where it is not continuous, not also discrete. Yeah, so okay, let me leave it at that.
Sir, is
Okay,
it y by 4?
pardon me. Why is this 1/4?
No,
Is
sir,
that what you're
is
asking?
it y by 4 the function defined?
No, I didn't understand. Can you ask that question again?
No, sir, like you have defined the distribution function, the second line, is it y by 4 instead of y by 2?
Where did I define that? Y by 4?
Sir, not definition, sir, like the
Oh,
computation.
oh, oh.
Yeah.
I don't see y by 4 at all.
Sir, the distribution, the computation of distribution function. And
GT?
sir,
Before that.
no, sir, after this.
After
Like,
this.
yeah.
Here? No, here
No,
I'm
sir.
just defining G of T.
Yeah.
And then where did I write y by 4? I can't see y by 4 at all.
Yeah,
I
sir, here. Here.
here
And,
y by 2. Y by 2, not y by 4. Y by 2.
okay, sir.
So here, you mean? Here this is y by 2. G of y by 2 gets mapped onto this interval.
Isn't it like,
Y.
isn't it equal to y by 4? The answer.
No, wait a second. Just a second, please. Just 1 minute. Um, oh, the interval 1/2. No, I just made that. So this, what is it doing? It is mapping the interval 0 to half to 0 to 1. Okay. Y can assume any value between 0 and 1, and I just have it. I will get y by 2. I will not get y by 4. You are asking why this is y by 2 and not y by 4?
Yes, sir.
Ah, okay, wait a second. Uh, yeah, okay, sorry. This, just, I have to think about that a bit. You see, what is the distribution function of x? Okay, uniform on this one. So this means that probability, this implies that probability x less than or equal to x. Ah, okay. When x is in this interval is actually equal to x, correct? Now, if I take y to be between 0 and 1, it is y is between 0 and 1, therefore y by 2 is between 0 and half. Whatever it is, so if you agree that this is y by 2, it has to be y by 2, not y by 4.
Okay, sir.
Okay? See, just apply the definition of the distribution function for a uniform random variable. Probability, this is valid if x is between 0 and 1. That's the definition of uniform random variable. Below x it is 0 and above 1 it is equal to 1. So that I'm not writing, I'm just simply writing this. Okay. It's not y by 4, it is actually y by 2 because probability x less than or equal to y by 2 is indeed y by 2. So, so in the interval, the probability that y lies, y is, capital Y is less than or equal to 1 has to be probability that x is less than or equal to half, which is actually equal to half. Because when you get half here, when y equals 1. So when y equals 1, you get half. Yeah. So it's okay. Yeah, please. I mean, it's quite possible I make sometimes some numerical error, but this time I think I'm absolutely okay. No problem. So the thing is, it is quite possible that just because you have defined your g of t, doesn't have to be the case that you always have g of capital X is also a continuous random variable. It could be discrete. You can make, you can play with this and actually get an example where y is equal to g of capital X is actually a discrete random variable. That also is very much possible. Anyway, let us proceed. Um, what I will do is, I always want to do more problems than spend time discussing theory. But nevertheless, for today, what I will do is first to discuss some theoretical aspects, uh, and then we will do problems. Okay. So this is the plan for today. Now, already I have talked about. So I have talked about this several times. Joint density function of of continuous random variables. Continuous random variables. You can have a vector actually x1, x2, blah blah blah. But let's just do x comma y. Okay, and you know that say denoted. So fx of x comma fx comma y of x comma y. Okay, and now what we are going to do is just like we did for single random variable, we can have a function of two random variables. Okay, so yeah, so let us consider this picture here, omega x comma y. Okay, maps it to the plane R2. I just draw like this, plane R2. And now from the plane R2, suppose I have two functions g, which I denote g comma h. Okay, and that again maps to a plane. It maps into the plane, and we will make suitable hypothesis. I will tell you what that hypothesis is in a minute. Um, so, well, actually, x and y may not map to the whole of R2, and I am just assuming that g comma h is defined on the portion on the image of this. Okay, so sometimes I may have to delete some line or some points. When I do example, things will become clear. And it also, this g comma h may not map to the whole plane. It may map to some region here. Okay, but this is a picture. Then the composition is a random variable which we would like to write as g of x comma y, h of x comma y. Okay, so actually, if you just call this equal to, I don't like to call it capital G and H, but let's just call it K for the time being. So this is K of x comma y. Okay, K takes values in R2 again. Okay, so this is a type of situation. Now you can wonder what happens. So uh, this, yeah. So well, actually, this so long as K is, let us say, a Borel, um, mm, yeah, Borel measurable function, that's the right language, or I don't want to make it technical. So, uh, so and under some general hypothesis, this will always be a random variable, no doubt. But we will assume that, so we will assume that G and H, sorry, this is comma, is such that G, okay, I just, G, yeah, okay. A bit difficult to say what I have in mind. Uh, yeah, so for okay, let me say, in order to develop this language, one has to use some terminology, but I'll avoid all these things such that for most points, the Jacobian of GH. Okay. So you may call this some u comma v is invertible. So such that at most points where x comma y in the domain of this is invertible. So this also I put within quotes, most points. Okay, I don't want to make it very precise. So basically what that means is that, so now, okay. So first of all, by saying this, I'm already implying that G and H are differentiable. Let us assume that they have continuous derivative, blah, blah, blah. So at least for most points. And at most points, the Jacobian is invertible, meaning, so if you write the Jacobian of u comma v with respect to x comma y, okay, and evaluate it at the point, some point x naught, y naught, this is of course a matrix. This is an invertible matrix. This is what I mean, invertible for most points, x naught, y naught. Okay, so now what we want to do is understand the distribution function. So we want to in this case actually even express, we want to express the density function or yeah. So under this assumption, then, so let me make this statement. Then whatever I wrote, k of x comma y is the joint density. Joint is a hmm, yeah. So this is a pair of random variables, right? Let me write this as u comma v. Write it as u comma v is a pair of continuous random variables, and we want to express the uh, joint density function. Joint density function of u comma v. So u, capital U comma capital V is what we want to do. Of course, in order to do that, you need to compute something, but I can tell you what the answer is. But first, let us just understand what is happening. So, so basically, so I am in this is like, let's call this UV plane, and my omega is here, and this is my u comma v that takes values in R2. Okay, and I have some blob here, so just shade it and call it some set B. Okay, now we want to understand what is the probability. So in order to be able to do this joint density function for u comma v and so on, first you need to be able to understand what is this probability that u comma v is in B. And the expanded version of this is probability of the set of all omega in omega such that, so u omega, v omega, okay, this takes values in B. Okay, this is a set for which you can talk about probability because of the assumptions we made. Okay, fine. So now this is same thing as saying, well, how was your u comma v defined? It had to factor through x comma y, no, x comma y, and it factors through this plane. So this was g comma h. Now this is same thing as saying probability of this is a crucial step conceptually. This is same thing as saying, okay, x omega, so I'll just simply write xy for that, is in this function g comma h inverse of b. Okay, so this is some function defined in a planar region, and that is getting mapped to here. So now when you, that means that you have to look at the inverse image. Yes, inverse image, and the inverse image may be some three blobs, not necessarily two. It could be like this, maybe one more blob, and these two, their union forms the full inverse image of this b. Whatever it is, I call that equal to a. So let a equal to full inverse image gh inverse of b. Then probability of uv in b is equal to probability of xy in A. Okay, so this is exactly the mean. And now you see, because you needed to write inverse. Now the assumption that we made that most of the time the Jacobian is invertible would tell me that the inverse set is something very nice. Okay, in fact, you can actually write our assumption on g comma h implies that so didn't want to write in such full detail, but implies that, let me say, uh, around most points, x comma y, or maybe x naught comma y naught, we can write x is equal to x of u comma v, and y is equal to y of u comma v. You can write it as functions of u and v, where of course u is equal to g of x comma y, and v is equal to h of x comma y. Okay, so you should be able to invert it. So remind you what I said about this in single variable case. Most of the time the derivative should be not equal to 0. If the derivative vanishes in an interval, then there is no way you can get a continuous random variable. So that's, yeah, okay. So now this means that okay, now so we can write this expression here in terms of u and v. So having written this, okay, this you can rewrite it as integral over a, okay, and fxy xy dx dy. And now you just do, so when you want to write everything in terms of u and v, you can write this following. Yeah, so w integral over a fxy dx dy, sorry, dx dy, no comma there. This is the same thing as double integral over b. So I can write here, uh, so fxy, yeah. So here you write here fxy of x as a function of u. So x of uv, y of uv, and then so this will become modulus of the Jacobian J. I will tell you what that is. Du dv. So this is from calculus of several variables, which you are probably learning this semester, but I need to use it anyway. Where Jacobian is this j of x comma y with respect to u comma v. Mind you, this must be a function of this. And why put modulus here? So I can give two reasons for it. One of them we encountered last time when I realized I was making a mistake because I forgot the Jacobian, the absolute value. So this anyway has to be a density, but Jacobian can take negative values. We only said it is not 0 most of the time. So you can write this in a neighborhood. So this is valid in a neighborhood. Then you have to say so around most points. So when I say around most points, meaning in a small neighborhood, but you can patch things together and then write it like this. Anyway, let me just write this very explicitly. Dx by du, partial dx by dv, and then partial dx dy by du, partial, so no comma there, sorry, dy by dv. This is the Jacobian. So mind you, it has to be a function of u and v. Okay, so this is okay, and you may have to take absolute value, and you will see examples where you are forced to take absolute value. It has to do with the orientation being reversed. That is the main reason why that happens. Anyway, so once you have this, now you have a formula for the density. So therefore, this yields the formula for the density of u comma v. So which is integral. So you are only interested in the very special type of this, which is minus infinity to u, minus infinity to v. So maybe instead of writing u and v, I should write, yeah. So okay, I write what I have, but here this will, yeah, I may have to change the labels here. This is something that, so so f of x of, I have to write s comma t now, and y of s comma t, Jacobian with absolute value as a function of s comma t and ds dt. Okay, this is it. Okay, yeah. So now let us work out some problems. But before I work out problems, I want to work out a problem immediately. Yeah, well, maybe I think I should. I'll just work out a problem. So maybe I want to work out the problem just after I talk about a few other things, mainly. So we will work out problems in a few minutes, but let us proceed further. Okay. So this is a very important formula. You can think of this is actually nothing but chain rule after all. So just remember, and in fact, this is called chain rule. Okay, chain rule for random variables. So yeah, so this is x comma y. Okay, so I can write this as I don't know what the notation I used. Let us call this yeah f. density, our notation for density is this. I don't want to change the notation. This is little v, okay, is equal to this. Okay. If you don't like to use k, u, I mean this f, just write maybe k just to avoid some confusion, you know, but I would write actually f, but if you drop the suffix, then it will lead to terrible confusion. So just for that reason, I will write f here, but k here. Okay. All right. So, uh, yeah. Okay. Hmm. Yeah, I want to talk about this one other notion that we came upon in the case of discrete random variable. I want to develop the parallel theory for continuous random variable. The discussion will be a bit brief, but we will work out problems. Okay, so conditional distribution. So suppose that fxy x comma y is the density of x comma y. Okay, is the joint density, just to be okay, joint density of this. Uh, uh, we want to define the notion of so so our aim is we want to define the random variable y given x equals x, but this makes no sense on the face of it because uh, of course this is defined to be what as as probability that y so so it's like so you are given x, no, so hmm, uh, y given x equals x less than or equal to y, this is equal to, but I will write something, you will see it is immediately observed. This is uh, given that x equals x. But this makes no sense because so makes no sense since probability of x equals x is 0. See, when you have continuous random variable, probability x taking specific value is always 0. Yeah. But you can make sense of it in the limit. So the right way to proceed is take, yeah. Uh, so correct way to do that is, so we therefore define probability of y given x equals x uh, less than or equal to y as, so limit, so as limit, okay, so h goes to 0, probability of y, sorry, y less than or equal to y, given that x is and this you can simplify and rewrite it. Okay, so let me write that. So Okay, I'll not derive this, but turns out. So this is the distribution function. Okay, so f of y given x equal to x of y is what we have written here. So when you finally analyze it, it turns out that this is minus infinity to y uh, fxy of x comma y dy divided by fx of x. Actually, I can push this inside the thing. It doesn't really matter because integration is with respect to y and x is like a constant. I have fixed my x. Okay, so this can be rewritten as. So how do you get this? After all, this is same thing as, let me just write one more step, limit h going to 0, probability of y less than or equal to y, and x less than or equal to x, then x plus h, divided by probability of x, okay, x less than or equal to x less than or equal to x plus h. Okay, now, well, that's how it leads to this in the limit. So mind you, when you write here x equals x here, so this is like, it's a constant. This x is not a variable. So I may as well write it. There are many ways to write this. Fxy of x comma y by fx of y, fx of x dy, and that gives you the density. Therefore, the density of y given x equals x is fxy x comma y divided by fx of x. Okay, you can also rewrite it in terms of integration because this is just marginal, right? X comma y, everything can be written in terms of the density joint density function. So minus infinity infinity fxy x comma y dy. Okay, so this is the density function, and as always, see this. Yeah, I can take as we did before. Let psi of x is equal to expectation of y given that x equals x. Okay. Now this is a continuous random variable with this density, and therefore we know how to evaluate it. Okay. So in fact, we can write this. This is equal to, what is this random variable? So you apply the definition, this becomes integral minus infinity to infinity y of, yeah, fxy. So this, we will write this as, okay, uh, f of y given x of little y given x. So that I can rewrite it like this, y given x of y given x. Okay, so this is dy by the definition of expectation. Okay, and of course you can rewrite it by just plugging in this value. I will not do that, but the main point is this is a function of x. This is a function of x. As in the discrete case, we obtain a new random variable. Okay, what is it? psi of x, and it is actually denoted as a expectation of y given capital X. Okay, this is all right. So this is a notation, and in fact, this is a definition of. You can think of this as a definition of the random variable expectation of capital y given x. Okay, and then the theorem. So the standard thing that expectation of psi of x is the same thing as expectation of y. In other words, that is expectation of y given x, exactly as in the case of discrete random variable, with obvious changes in the proof. That's it. Okay. So I don't want to discuss the proof of this, but you know, so the proof involves what? I mean, it is simply going to involve how to write expectation of psi of x. So the key point is the following: expectation of psi of x is integral minus infinity infinity psi of little x times, okay, fx of x dx. Now you substitute for psi of x, simplify and do this, and you get the answer. Okay, you get what answer? You will get this. Okay, so that's the thing. And now I'm ready to work out some problems uh, involving all these concepts. Okay, so let me take some fresh page. I wrote down some problems here. So this is given in the book. Actually, I'm taking problems mostly from books. Let f x comma y of x comma y is equal to c times x times y minus x times e power minus y 0 less than or equal to x less than or equal to y. So should I write less than or equal to? I suppose I can write that. And this is finite. Okay. Y is any finite quantity. So find C, the constant C, so that fxy uh, is the density of the joint density. Okay, I forget to say that joint density function of x comma y, and then find the density function of x given both, actually x given y equals y and y given x equals x. You can find both. Okay, so the first question. And how do we do this? So just, okay, so in order to find C, we integrate, we find double integral. Yeah, you integrate it over the. So first of all, you have to check that, c times whatever function I have actually is a positive function. Yeah, because I have written non-negative function y minus x, but y is always bigger than or equal to x, and x is bigger than or equal to 0. So all the three factors here are non-negative quantities. So c will be some constant which we will find out. So okay, so that's why it's enough to just write this. We find that 1 by c is equal to this quantity minus infinity infinity fxy. Yeah, it is understood that when something is outside that range, it is actually this fxy is 0. We don't, I mean, by convention, we don't say it explicitly, okay? It is understood, dx dy. Unless there is a possibility of a confusion, we don't say it. So this is x. So, okay, now, yeah, you can do this in any order, of course. Um, okay, so y, hmm, I can do this. Maybe I just do this x is from 0 to infinity and y is from, I don't know which one is easier.
So I think that doing X will first will be easier.
Hmm. Yeah, okay, let's do it that way. First, with respect to x. So it's better to shade this region. It's very simple to shade it. It's only in the first quadrant, and that too, x is less than or equal to y. So it is like this. Okay, and now, so this is the shaded region. Okay, this is the region that you get here. Y is bigger than or equal to x. So, okay, fine. Okay. So, yeah, because this e power y times, so x ranges from 0 to, I think it really does. Okay, we will do it. Either way, it doesn't really matter. 0 to y, y goes from, but x goes from 0 to y, then y goes from 0 to infinity. Yeah, okay, that's right. So now you write this x times, okay. So this is what I wrote is logically imprecise. Hmm. So c times, okay, x uh, xy e power minus y minus x square e power minus y dx dy. Okay, so I think either way it's a slightly messy calculation. You will see why. So when I do this with respect to y, so e power y, so here I will get x square by 2, uh, and here I will get x cube by 3. Okay, but these factors I need to keep track of y e power minus y between the limit 0 to y minus, what is it? This x cube by 3 between the limits 0 to y. Okay. So I left out that e power minus y factor. Let me write it here like this. And dy, finally. So this whole thing uh, is equal to c. I don't think it simplifies so much. But anyway, so I will always get y cube So here also I will get y cube 1 half minus 1/3, that is 1 by 6. So I get 1 by 6 y cube e power minus y dy. Yeah. And it turns out that, this quantity y cube e power minus y dy, it turns out that this is actually equal to 6. Well, that's what I calculated. Turns out to be equal to 6. Therefore, C equals 1. I think C equals 1. So I don't think I made a mistake. I tried this today. You have to use this UV formula, product rule for integration. When you do that, you get this. Okay. Maybe if you do it the other way around, it may be easier. I don't know. Anyway, let us proceed. You can check this later. Now, I want to do the computation. Capital X given y equals little y. Okay. So, all right, one can just simply use the formula. We don't like to do that, but just to save time, okay? Just to save time, I will use a formula. This is something I don't usually do, but okay, what is the density function? It is just this fxy by integral minus infinity to this. Just do this. This is the thing, okay? So integral, therefore what I need to do is, yeah, compute this. Okay, so in order to, let me say here, in order to compute uh, x given y equals y, we need fy of y, no? So fy of y is integral. Okay, so y ranges from where to where? So y is between x and infinity. In x and infinity. X to infinity. C equals 1. So if I remember, it is x times y minus x times e power minus y. So this is a function of, this has to be a function of y. Something is wrong here. It must be, so in this formula, okay, nothing wrong, but this must be, okay, sorry. This is perfectly okay, no problem. Dx. What did I do? So we need to compute the density function. Okay, so first of all, we should compute dy. So dy, in order to compute dy, okay, so we need to integrate it with respect to x, fxy. If you recall, this is, so, okay, let me write it because so just write fxy, xy, dx, and you write simply minus infinity. And it's understood that, well, the f is suitably modified. Okay. Now, so mind you, integration is with respect to x because this must be a function of y. If we make a mistake, we'll find out ourselves. So what is the range for x? Range for x is 0 to y. 0 to y. Okay, so it is 0 to y, and here whatever that function was, x, y minus x, e power minus y, dx. And now treat y as a constant, okay, because y is fixed here. So e power minus y comes out, and then I have xy minus x square. That's an easy integration. So y times x squared by 2 minus x cubed by 3, and between the limits 0 to y. Okay, and when you do that, you get e power minus y. And what is this? So each time I get y cube divided by, so y cube times 1 by 6. So times 6. Okay. Therefore, now I am ready to write. Therefore, fy given x of little y. Sorry, now we are doing x given y. So x given y equals y is, I should write it the other way around. X given y is equal to fxy x comma y divided by fy of x comma y. Fy of x comma f, yeah, this is it. So this is, we found out just, we are given this x times y minus x e power minus y, and this we just now found out to be uh, here e power minus y. So this y power 6. I hope it's correct. Yeah. So I think it will be okay. So divided by uh, so e power minus y power y cube, e power minus y. Here I have 1 by 6, so that I'll write here in the numerator. This is equal to 6 x times y minus x, y power minus 3. Okay. All right. Now, similarly, you can find f y given x equals x. The formula for that is indeed fxy of x comma y divided by fx of x. And I just write down only the very brief sketch of that. Fx of x. So this is just a computation of the marginals. So minus infinity, infinity. You write the formula in the most general form several times so that you don't forget it. Things are all easy, but it can get very confusing. So mind you, this time integration is with respect to y, because you have to have a function of x, and you can treat x as a constant so far as this integration is concerned. So it cannot be dx here, it has to be dy. These little things which are very obvious are very helpful. In case you make a mistake, you can find out by yourself. All right, I'm not going to do this. So maybe I do some other problem. Uh, you can complete this at home. Uh, yeah, okay. I want to do another problem. So let me do this. Okay. I want to do two problems. Let's see if I have the time for that. So suppose that fxy x comma y is the joint density of continuous random variables, continuous random variables x comma y, random variables x comma y. Find the okay. Actually, the answer is given, and in fact, it's worked out in the book, but it doesn't matter. I don't know if it's yeah. Find the uh, density function of xy. Okay, u equals xy. Yeah. So usual hypothesis, uh, book never talks about these things, and sometimes, in fact, I found some incorrect statements also in the book stated as theorem. But anyway, um, so our usual hypothesis is that hmm, yeah, I suppose in this case it's okay. Anyway, let's just write this. Let me tell you what the how to approach this problem. You choose one other variable, okay, all right, so that you will be able to express x and y. So one other random variable v, and so that you can express x and y in terms of u and v. So the most natural thing to do is take y equals v equals y. Okay, that clear? All right. When you do this, then I can write. So you see, I yeah. Here is a situation. So consider g of x comma y to be xy, and h of x comma y, it depends only on y. So that so putting these two together, okay, k is equal to, so yeah, g of x comma y. Let me remove this k, it could be confusing. Just a pair of random variables, and h of x comma y is the random variable that you need, u comma v. One of them is what you need. V is something that you artificially introduced, but it's most convenient because you can express. So note. So you can write. Okay. Well, actually, you can write the Jacobian and make the test that I told you, but directly also write this as, consider this as u and this as v after all. Okay. So I can write, note, x is equal to u by x is equal to u by v, and y is equal to v. Okay. Therefore, Jacobian of x comma y thought of as a function of u comma v. So I have to do this partial. So with respect to u, I get 1 by v. And here, with respect to v, I get minus u by v square. Okay. And then with respect to y, so y with respect to u, I get 0. Y with respect to this, I get this. And therefore, what is the Jacobian? Determinant of the Jacobian is 1 by v. And 1 by v equals 0, so vanishes on, well, so, okay, actually 1 by v doesn't vanish, but it's undefined. If you find the Jacobian for the other one, u comma v, then you will find something, the zero locus of this. You can do this, but let me not worry about that. So it's undefined on v equals 0. Okay, but v equals 0 is very much there in the domain, and that corresponds to y equals 0, x arbitrary. This is what I said on a small set. So you see on the xy plane, just let me take 2 more minutes and explain this. So on the xy plane, so y equals 0 is x-axis. Along this, the Jacobian, the function is not invertible. On the uv plane, v equals 0. V equals 0 again corresponds to this. Okay, so it's only a small set, meaning it has measure equal to 0, right? Okay, so it doesn't contribute to probability. Okay, so having said all the right things, now it's just a routine matter. Therefore, to compute the joint density function of u comma v, the joint density function of u comma v is, okay, so here you write fx. We don't know, this is a very general, I gave a general thing. So x comma y, where now you can write x in terms of u and v, right? X was u by v and y was v. Now you must write here that absolute value of the Jacobian, which is 1 by v. So this is the main thing. Okay, so it could be that v is negative, and then if v is negative, then this, you see, fxy is always non-negative, okay, or essentially non-negative. Anyway, we assume things are continuous, then it is always non-negative. This 1 by v, however, can be negative. If x and y are having opposite signs, then v will have negative sign, okay? Sorry, if y is negative, then y equals v, therefore this will be negative. So I need to have this. So this is the main thing. Okay. I'm out of time. I wanted to discuss one other example, but as usual, I don't have time. I stop here. If there is any question, I'll take 1 or 2 quick questions. Otherwise, we can stop.
Thank you, sir.
You're welcome.
Thank you.